doublet is a pair of source and sink placed along a line such a way that the strength of the source and sink are very high, and the distance of separation between them is tending to 0. So in this case, you will get a doublet, and you apply the method of superposition of a source and sink, and then by applying the limit. So you will get the complex flow potential for a doublet as mu by z, where z is a coordinate of any point and the doublet is placed at the origin. So that's a doublet which is placed at the origin. So the center of the doublet coincides with the origin of the coordinate system. So Z gives you the complex variable, which is which represents the point, any point x plus iy. Z is equal to x plus iy, and the function of Z is mu by Z. And you also know that uniform flow can be represented by the complex flow potential u infinity into Z. So that is there is no angle, that uniform flow from everywhere like this of the same magnitude u infinity and then parallel to the x-axis, or it is approaching perpendicular to the y-axis. That is Fz is equal to u infinity into Z. And for this derivation, okay, first of all, we are trying to see what happens when a doublet combines with a uniform flow. So what is a doublet combining with a uniform flow? So method of superposition gives you the complex flow potential Fz is equal to u infinity Z of the uniform flow and mu by Z of the doublet. Okay, our aim is to separate this into imaginary and real parts so that we can find out the flow, scalar flow potential and the stream function. So the real part gives you the scalar flow potential, and the imaginary part gives you the stream function. So you write in polar coordinate system, Z in polar coordinate system is r e raised to I theta, mu by r e raised to I theta. So just e raised to I theta comes on the numerator, e raised to minus I theta, which is cos theta minus sin theta, whereas e raised to I theta is cos theta plus I sin theta. And the terms containing I, you take it out, that you can write as psi. So psi is u infinity into r into sin theta, that is excluding I. Here also excluding I, you are having a mu by r and sin theta, and sin theta is common, you take outside, which is u infinity r minus mu by r. So psi is a function of r and theta. You obtain psi as a function of r and theta. If you want to write psi as a function of x and y, also you can write. So you only change r is equal to, for that you change this r is equal to s squared plus y squared, the whole raised to half, right? And okay, this r also like that. So sin theta is equal to y by r. Y is equal to y by sin theta is equal to y by r. Y by r is s squared plus y squared, the whole raised to half. Okay. Or you can write, okay, this y by s squared plus y squared, the whole raised to half. That way you can write psi as a function of x and y also. Right. Now let us see what is the streamline corresponding to psi r theta equal to 0. That is psi r theta, substitute psi r theta is equal to 0. That is possible either by taking sin theta is equal to 0, or if this is 0 also, it can be satisfied. So in which case u infinity into r is equal to mu by r. That is the condition where psi becomes equal to 0. That's the condition. So this gives you r squared is equal to mu by u infinity. So okay, r squared is mu is the strength of the doublet, and u infinity is the magnitude of the uniform flow. So mu by u infinity is a constant. So psi is equal to 0, psi will become equal to 0 on r squared is equal to a constant, which is a circle. So this is a circle. So the circle like this, a circle like this. Okay, circle like this. So this is a circle. So and other condition is 2 points, this point and this point. That is, this is theta equal to 0 and this is theta is equal to 5. So that's also. So equation of streamline psi is equal to 0 is r squared is equal to mu by u infinity is a constant. Is a circle of radius square root of mu by u infinity. So what is the meaning of a streamline? No fluid cross this circle, this line or circle. So what is the resulting flow? The resulting flow is identical to the flow past a cylinder placed in a uniform flow. So you place a cylinder in uniform flow, get like this. So the radius is square root of mu by u infinity. Or you can find what is the strength of the doublet. What is the strength of the doublet required for making a cylinder of radius r in flow? Right. So you can bring in a cylinder of radius r in flow, for which what is the strength of doublet is r squared into u infinity. So any doublet would not give, right? You have to place a doublet of a particular strength corresponding to the radius of the cylinder and the free stream velocity. So we get the flow past a cylinder of radius r by placing a doublet of strength mu is equal to r squared into u infinity. So what is the resulting complex flow potential? Now you substitute for mu, you will get Fz is equal to u infinity z plus r squared u infinity by z. So u infinity is common, you take outside, z plus r squared by z. So where r is the radius of the cylinder. So this gives you the complete thing about flow past a cylinder placed like this in a uniform flow. So the fluid will be turning like this. Then there's a tangential motion is there. So there is a radial motion and tangential motion. So you can write okay. Now our aim is to find out the velocity components. So find out the velocity. So this is about complex flow potential. That would give you the scalar flow potential and the stream function expressions. Right. So, now complex velocity. We also studied complex velocity. So complex velocity, okay, in polar coordinate system, f dash z is into u raised to I theta is equal to ur minus I u theta. This you should remember. In Cartesian coordinate system, f dash z is equal to u minus iv, where u is the horizontal component of velocity and v is the vertical component of velocity. In polar coordinate system, it is f dash z into e raised to I theta is equal to ur minus I u theta. Now you have your Fz is equal to u infinity into z plus r squared by z. So find out f dash z. F dash z is equal to u infinity into z derivative gives you 1 plus r squared by z will give you minus 1 z raised to minus 2. So r squared by z squared. That is a derivative, simple differentiation with respect to a single variable z. Right. That would give you f dash z. Now f dash z into e raised to I theta is equal to u infinity is 1 r squared. This z squared, z is r e raised to, you can write r e raised to I theta. Then what is that squared? Is equal to r squared e raised to 2 I theta. So r squared e raised to 2 I theta into this e raised to I theta. So that is u infinity into e raised to I theta minus r squared by r squared. There is a 1 e raised to I theta will cancel and you will have a remaining 1 e raised to I theta in the denominator. That becomes e raised to minus I theta. And that can be equated to ur minus I u theta. In that way, you can write the real part is the radial velocity. Radial part is the radial velocity. So radial part you write u infinity into, here there is a radial part cos theta. So not radial part, real part. Please, okay, okay. It's not radial part, but real part. U infinity cos theta minus r squared by small r squared into, here the real part is also cos theta. So u infinity cos theta into 1 minus r squared by small r squared. Now you look on the surface of the cylinder. On the surface of the cylinder, this small r is equal to capital R. So it would become 1 minus r squared by r squared, capital R squared itself, that is 0. That is radial velocity equal to 0 on the surface of the cylinder. So that is clear because the cylinder, there no fluid will be penetrating. Radial velocity is equal to 0 on the surface of the cylinder. So that is coming up. Right. So this whereas at any other point outside the cylinder you will have a value of ur depending upon the radial location and the angular location. So its ur is a function of r and theta. Similarly, the imaginary part you write. So here u infinity into sine theta is the imaginary part. Here r squared by r squared. Here minus sine theta is the imaginary part. And that minus and this minus will become together plus. So u infinity sine theta into 1 plus r squared by r squared. So this is the tangential component of velocity. So there will be tangential motion. There will be some tangential motion of fluid particle like this. The fluid particle will be moving over the surface of the cylinder. That will make the flow motion as something like on this tangential surface of the cylinder, tangent to the cylinder. So what is the velocity? You can find out different points. So, okay, this is at any r and theta, but on the surface of the cylinder, what happens? So u theta on the surface of the cylinder is equal to u infinity sine theta into 1 plus r squared by r squared. That is equal to twice 2 u infinity sine theta. This is the tangential velocity on the surface of the cylinder. And you measure the angle from here, theta. This point is theta is equal to 0. This point is theta is equal to, this point is theta is equal to pi by 2. Right. This point is theta is equal to pi. So like that, if you look at those points, when theta is equal to 0, you have u infinity r0 is equal to 0. So at this point, fluid velocity is equal to 0. So this point is called a stagnation point. It's called a stagnation point. Right. Now theta is equal to pi. What will happen? 2 into u infinity into sine pi by 2. Let us take it as pi by 2. So sine pi by 2 is 1 twice. So you'll have a twice of the free stream velocity where at theta is equal to pi by 2. That means at this crest point, right, the tangential velocities 2u infinity. Let me check the units. Okay, there's a mistake from the units. So this is all minus u theta. This is minus because minus iu theta. So not the imaginary part, negative of that. So if I want u theta to be written, it has to be like this. So this has to be like this. So this will be like this. There is a negative sign. So minus 2u theta. Minus 2u theta. So what do you mean by that? Okay, it is minus. So actually, this is the tangential direction. The positive tangential direction is in the anti-clockwise. The measure of the theta is measured in the anti-clockwise direction. So at this point, the positive tangential velocity is like this. So what do you mean by minus 2 theta? What does it mean? Minus 2 infinity u theta. That means the velocity is like this. Because the free stream is coming like this, it moves like that, and here you will get this 2u theta. Right? The magnitude of velocity is 2u theta, but from tangential point of view, it is minus 2u theta. The tangential direction point of view is minus 2u. Right? That's also clear. So you have this minus 2 infinity. If we look at the magnitude of the velocity, there is no radial velocity. The magnitude of the velocity is twice u theta, twice u infinity, twice u infinity. So it's like that. When again theta is equal to pi, minus 2 infinity sine theta, minus 2u infinity sine pi is again 0. So theta is equal to pi. Also, the velocity becomes equal to 0. This is also another stagnation point. This is also another stagnation point. So the first stagnation point that is facing the free stream is called forward stagnation point. And this one at the downstream is called rear side, rear stagnation point. Rear side stagnation point. So forward stagnation point and rear side stagnation point. So now we have come to all kinds of velocity components. Maybe if you want, you can convert into Cartesian components also. Somebody wants to plot it, you can plot it. So this is the velocity variation you will find when the cylinder is placed in flow. And this is incompressible irrotational. So Bernoulli's equation is applicable. So the velocity is known. You can find out the pressure also, right? So the magnitude of square of magnitude of velocity. Square of magnitude of velocity. So in Bernoulli's equation you are having the magnitude of velocity is this by 2. One term, that is 2u infinity squared. So the pressure at any theta plus P by rho So this way you get the pressure at any point. So P theta by P theta by rho plus half u squared equal to or half I am 2 u infinity squared sine squared theta. This is a constant. This is a constant. And suppose in the free stream, suppose the pressure in the free stream as P infinity. That is at a point which is not affected by the cylinder, the pressure is P infinity. So you can write as P infinity by rho plus. So that the velocity is U infinity. So here it is. So that way we can write P minus P infinity by rho is equal to U infinity squared by P. Or P minus P infinity by half rho U infinity squared. P minus P infinity, that is the difference in pressure divided by half rho U infinity squared. Half rho U infinity squared. So this is the inflow kinetic energy. Inflow kinetic energy per unit joule. Per unit joule. So half rho infinity is that is inflow kinetic energy per unit volume, and unit of P minus P infinity is also same. So you will get a dimensionless quantity. P minus P infinity divided by half rho infinity squared is a dimensionless quantity, which is called the coefficient of pressure. P is equal to 1 minus 4 sin squared. So this is the pressure coefficient, or that gives the pressure distribution over the surface of the cylinder. So you can find out where the pressure is maximum, where the pressure is minimum. Where the velocity is minimum, you'll have a maximum pressure. Where velocity is maximum, you'll have a minimum pressure. So when theta is equal to pi by 2, you're having maximum velocity. So what is the Cp over there? Cp is equal to 1 minus 4 minus 3. What is when theta is equal to 0? It is Cp is equal to 1. Theta is equal to pi, Cp is equal to 1. That way you can plot the variation of the Cp over the surface of cylinder. So you can plot the variation. So at this point, maybe at this point, this point. So this may be 45 degree, theta is equal to 45 degree. This theta is equal to 0, this theta is equal to 90. Like that, you plot that, right? So I will stop the recording and we'll have a discussion